Okay. So, ladies, Gold Rush task out ASAP, please. Was this problem 4x plus 3 squared? Is that the right equation?
Yes.
Right function, okay. So,
With that one, actual.
now, it said f of 1. Now, it does worry me a lot because I saw exactly the same language for a lot of us, which means some of us heard others talking and put this answer down, but this is something we got to know. This is one of the most fundamental pieces that really hurt some of us on the parent function stuff. If we had just taken the time with this, parent functions, not necessarily the transformations, but the parent functions would have been easy peasy lemon squeezy. So, what did a lot of us do with that 1 right there? We need, so you said you add the 1 to x? There we go, right? So literally, what is that 1 taking the place of? X. We're saying x is equal to 1, so substitute 1 in. So we get 4 times 1 plus 3 squared. That's it. Simplify it. What's my order of operations? Which, by the way, you could just put this into the calculator, but what is my order of operations? Multiplication. Well, what's before multiplication and addition?
Parentheses.
Your parentheses. Remember, if you need to group something, okay, so then exponents, multiplication and division, addition and subtraction. Remember, because I will point this out, are you going to square before anything else right here?
No.
No, because even though exponents come before multiplication and division and addition and subtraction, we've grouped these together, which tells us to simplify inside first, then square. So we get 7 squared. Now y'all need to remember, what does it mean to square something?
1 time.
So 1 times 7 times 7, right? Because we started at 1, we multiplied by 7 twice to get a total of 49. That's it. Like, and I know some of us are like, Mr. Kenny, I can't do that in 2 minutes, and I end up giving y'all way more than 2 minutes, but that's something we should be able to do, and honestly, way less than 2 minutes. Realistically, how long should that question take us?
30 seconds.
30 seconds-ish, right? Just substituting that stuff in, okay? Put on what you're working on over there.
You owe me 5.
Say again. Miss Lightfoot? But this is Algebra 2 right now. She'd be upset if you were doing my class, my work at her class, right? Yes, she would.
She actually would.
She actually would.
She actually wouldn't.
She actually would. I'm taking Mr. Kenny's side today.
Okay, well, I don't care.
I don't care.
You owe me 5.
I need you to learn
You owe me
this.
5.
Complete that homework assignment, whatever it is outside of
I owe
class.
3.
Alright.
Where's Kenny get the door?
Okay. What was I going to say next?
I don't know.
What I want to point out with this is parent functions. To help y'all get better at parent functions, remember, if I tell you, hey, y, or let's say f of x equals the, let's say, x cubed, all you got to do is substitute your inputs in. Literally, what am I saying x is right now? -2. X is 1 and 2. This is what I kept trying to tell y'all. Like, you clearly can substitute into something more complicated like that. Take the time
What are we
to
substituting?
substitute your inputs in. If I take -2 and like, if you had taken the time, and I told you on the test, if you needed help with calculations, or Mr. Anderson told you, if you needed help with calculations with something like that, we would tell you the answer. But you had to show it substituted in. I needed you to know I can at least substitute this in. -2 times -2 is 4, times -2 is -8.
Miss, can you think my next week will have our test?
Some point next week, yes. So,
Do we substitute in for the f of x equals?
you substitute in for x. And then what the output is your output here.
I'm talking about that equation.
What do you mean?
4 + 3, 3 squared.
What about it?
Am I doing something? Yeah, it's good.
Kenny,
That was our bill, that's.
I know that.
that's literally what we talked about for 4 minutes already. Right?
Well, he wasn't on that. Oh, there's no water.
Oh. Yes, you substitute in. Okay. So let's continue with what we're gonna be working on today. So, let's do a recap of the Gold Rush task. I forgot to actually put in here, we're gonna do some practice with identifying the different types of functions. What are the 3 major types of functions we have studied? Not necessarily the parent functions.
Linear.
So linear, exponential, and
Quadratic.
quadratic is what we did yesterday, right? So what we're gonna take some time doing is just identifying the 3 major types of functions in graphs, tables, and equations. And so this is from yesterday, being able to identify a quadratic function, right, in tables, graphs, equations. Identifying all features of a quadratic function in a graph. What are the features of a quadratic function again?
Wait, you said what it
Oh, x-intercepts,
Y
y-intercepts,
line of symmetry,
line of symmetry,
concavity,
concavity, and vertex. Right. Guys, when I say features of the quadratic function, you need to know those things immediately. Like, you have to make sure you know, hey, this is what Mr. Kinney's looking for. Not just Mr. Kinney, math people. Like, when we're talking mathematically, we're talking about the features of a quadratic function, those are them. They're highlighted in blue, because that was the goal yesterday, to learn those features. And then concavity. Okay, so quick Gold Rush recap. So here's what I want to do is I have it over here. I want to emphasize a couple of details that we need to pay attention to, and Mr. Anderson may have hinted at them, but I want to make it more explicitly clear, which is why you should have Gold Rush out to add stuff onto the back if you are missing any of these details or all of these details. Huh?
Got that right.
Yes, but move your desk around so that you can see what I'm talking about. Okay, so remember the whole goal of that lesson yesterday was be able to identify a quadratic in any of those mathematical representations, okay? So if I have a graph, just to help you out, put on the back side, there's a specific place to take notes. Okay, just trying to, it has more space. Okay, so, I mean, you could have it turned over to take notes.
Why you talking to me like that?
Because you don't even have it flipped over.
I ain't got nothing on there.
That's not a good argument. I literally got frustrated with everybody in class 10 minutes to go in class because we didn't take notes, and then you still didn't take notes? It sounds like you're trying to play dumb games. You know what happens when you play dumb games? You win dumb prizes, okay? The dumb prizes maybe not being as successful as you should be. Okay, so first things first, when we look at this graph, so this is a graph of all of our inputs and outputs, looking at the base and the area. So the base length of our plot of land against the area of that plot of land. What about this graph told us we had a quadratic? Okay, right, we need to recognize this graph is a what again? Parabola. So the function is quadratic. I want to point this out. What word did I not use up here that a lot of you like to use? Yeah, there's no it up here, is there? Okay? I'm being clear in my communication. There's no it because it can mean a million different things. The graph is a parabola, so the function is quadratic. Like, we need to recognize that. When I see a parabola, I know the function is quadratic, okay? So what's this point up here? The vertex. And this statement right here was actually from someone in 4th block, and so I do want to point this out. The clean way to know the vertex is it's the what for the graph? Turning point, right? There's a much more precise definition that when you get into higher level mathematics that you go into, because there's a thing called a vertex, a directrix, a focus, it's a pain, but you don't have to worry about here. I just need you to recognize the vertex is the...
So the top.
Does it have to be the top?
No. What's the max? So what's the max?
Because it sometimes is the max when the parabola is concave down, it's a maximum, right? But when the parabola is concave up, it's a minimum. But it's the turning point, okay? Mr. Anderson didn't do this. I like this. I know Miss Williams does the same thing. It's just a little rhyme that my math teachers in high school taught me. Concave down like a frown, concave up like a cup. And we're going to talk about when it'll be concave down and concave up later today. Turn the temperature up just a little bit. Okay. We got our x-intercepts. Please remember an x-intercept specifically is when what is true.
Wait.
How do you know when we have an x-intercept?
When something x-axis.
So when
It crosses.
when
When
Function.
the
function
crosses the x-axis.
crosses, what's that more mathematical term? You're not wrong, but the more mathematical term. It what?
Dialects. No, it's
It intersects the
Intercept.
x-axis. Okay, an x-intercept is when the function intersects the x-axis. So then what's a y-intercept?
so wise.
The function
Intersects the y-axis, right here. Notice this point was both an x-intercept and a y-intercept because it's intersecting at the origin, okay? And then what's this line right here?
The line of symmetry.
The line of symmetry. That line of symmetry is wicked important because it's going to help us recognize and identify different things. Notice literally, see that point right here? KB, you with me? Your hand or your face is literally in the palm of your hand. And you got 0 notes down. Okay, so this point right here, isn't it the same distance or roughly the same distance to the other side over here? Same exact outputs, right? But it's been reflected across that line. That's really, really, really important. So we should have those different things down. So the graph is a parabola. We have that vertex. We have that line of symmetry. We have our x-intercepts and we have our y-intercepts. You got to know all those different features and be able to identify those different features of that parabola. Does anyone see a red marker that was on the floor over there earlier today? Like a red expo.
They're right here.
Thank you. I really need them to give us our teacher money so that I can buy some more expos. I've already bought so many. It's expensive.
How much do they got?
I mean, like a decent box is like 30-something bucks, and I have to have already spent close to $200 on the classroom just buying supplies because they haven't given us our money yet.
That's how I get like a card.
But it doesn't. We don't get it till October usually, and now we're at the end of October, and they still haven't given it to us.
It's scary,
So, just things happen. All right. So, you need to have at least a sketch of that parabola. You need to identify the different features. But let's look now at this table, okay? So, in a graph, we know we have a quadratic when we have a parabola. But in this table, there's a really special relationship that I want us to make sure is clear that we see. And I know Mr. Anderson talked about it. I want to slow it down just a hair so we can talk about it a little bit more deeply, though. Remember, with a linear function, what type of rate of change did a linear function have?
Additive.
Not just additive, it was constant additive. What type of rate of change did an exponential have?
Constant multiplicative.
Okay, thank you, right? It's still up there, constant multiplicative. Quadratics don't look like they have a pattern at the beginning, but they actually do, and it's actually a unique pattern building on what we did over there. So, in order to go from 0 to 225, what do we have to do? We had to add 225, right? All right, to go from 225 to 400, how much was added?
225 to 400 was
175.
It was plus 175. All right,
How?
we'll take 225 and add 175 to it.
How do we know to add 175?
I looked at it.
Then plus you can, if you don't, you can subtract. Well, I do the big number, so I won't
Yeah.
get negative, but.
Well, and you also want to do the next number and subtract the previous number. Okay, so it's not always the biggest that you do first, but it is the next number minus the previous. That's how you know how much to add. Because, let's say it this way, if I take my previous and I add my constant difference, I get the next. to find that I subtract. So it always has to be next minus previous. Okay. How about to go from 400 to 525?
125.
That's plus 125. 525 to 6.
75,
Okay. 600 to 625.
125.
And so this right here really is why it's important that we do next minus previous, because if I do bigger minus smaller, then I just get 25. But I'm not adding 25, I'm subtracting 25. But if you do 600 minus 625, you get that. 525 minus 600.
Wait, so never mind.
So this is my rate of change there. It's definitely not constant, is it?
No.
But is it still,
It's not constant, because it's not like,
It's not the same numbers, but.
right, but what does that word constant literally mean? It means it stays the
same.
same, okay? Is it additive though?
Yeah.
100%. But look at the red numbers. The red is my rate of change. So notice this is not a function right here, but in red I have a rate of change. But look at the red. What's happening to the red every single time?
They going down, I think.
It's going down by 50. Tell me a more mathematical way to say that.
It's decreasing about 50.
It's decreasing or subtracting by 50. 225 minus 50 is 175, isn't it? 175 minus 50 is 125. What's 125 minus 50? 75 minus 50. 25 minus 50. Negative 25 minus 50. Notice, that red rate of change, it was not constant additive. But what is this green?
Constant.
Constant what? Additive. I know it's subtracting, but remember, subtraction is just a type of addition. So this green here is constant additive. Now, please hold on. I'm not going to call it a rate of change. I'll explain why in a second. Because, well, here's what I'm going to say it this way. This is the rate of change.
Oh,
Okay? This is the rate of the rate of change, which is a little weird, but that's why I don't call the green a rate of change. But this is constant additive. Now, Victoria, remind me, what type of function had a constant additive rate of change? I will tell you, it's not on that sheet. I'll come back to you if I need to in a second. Walter, what type of function had a constant additive rate of change?
linear.
Okay? Linear function had a constant. Look over there, I need y'all to remember. There's two functions that have a constant rate of change. What are the two functions?
Oh, linear and exponential.
Linear and exponential. Which one was constant additive?
Linear.
Linear. Okay? So Victoria, which type of function had a constant additive rate of change? Linear. We cannot forget that. So the fact that this is constant additive right here means, how could I describe this red? Actually, let me point this out first before I ask that question again. What are we literally doing with each of these numbers? Adding or subtracting, but subtracting is a type of adding. So this rate of change, is it additive?
Yeah.
Yes. But is it constant additive?
No.
No. But the red has a constant additive rate of change. So how could I describe that red additive rate of change?
Describe.
Thank you, Rihanna, for just looking at him like that. Guys, how could I describe this red if it is constant additive?
Okay.
Yes, you can.
What do you mean by describe?
We talked about it
Okay.
yesterday.
Finney, remind me, what type of function had a constant additive rate of change? Linear, okay? So how could I describe this red if it is constant additive?
Linear.
I could say the red here is linear.
But it's switching. It's going to negative.
Right.
But it's still linear because
Yeah.
you got a constant.
So remember, so what I'm trying to point out is, if this is constant additive in green, how am I going to describe the red?
We don't know.
Linear.
Linear, my guy.
Oh,
It's right there.
Oh.
What type of function had a constant additive rate of change? Linear. So what am I going to call this red rate of change?
Linear.
Linear, but it's additive and it's the rate of change. Notice this is not a linear function, but it is a linear additive rate of change. When you see constant additive, what is to the left is linear. So what type of function did we say this purple was again?
Quadratic.
It was quadratic. So what does a quadratic function have? Quadratic functions
Have linear
Have-
additive rate of change and a constant additive rate of change.
be careful, just have
Linear.
linear,
Active.
additive
But it's not a rate of change?
rates of change. It is a rate of change, but we're not gonna say constant. The reason we know this is linear rate of change is because its change is constant. So we're not gonna say it has a constant additive rate of change. It has a linear additive rate of change. That's what's happening there.
Too many linears. I don't know. It's too many rate of. I understand it.
Jaden, move your head.
Each function, so if you need to stand up so you can see, you can. Jaden, if you want to scoot to the side so others can see, you can. But Finney, what a linear function has what rate of change?
Constant additive.
Okay. If something is constant additive, then we can say it is also what? That's it. There's actually not multiple things going on. I see constant additive, so I know it's to the left is linear every time. If I have a constant additive rate of change, I have a linear function.
So we get 50. Okay, we get 50 each time because we subtract it.
But the big difference, let me say it this way. If it has constant additive, it's linear. The question is it a linear additive rate of change, or is it a linear function? This is a linear additive rate of change. That's what tells us the purple is quadratic.
How do we write the equation?
We're not there yet. Okay. Because remember, all we've talked about is how do we identify it as a graph, and how do we identify it as a table. Okay? Now, a couple of things I do want to point out about this table is, does anyone recognize this point from where we saw it on the graph?
Yeah.
Kind of. It's the what? That's my vertex, isn't it? So what do we have around that vertex? There's an S word.
Sequence.
What do you have around the
A
vertex?
line of symmetry.
So there's symmetry, right? A telltale sign of quadratic functions is the symmetry. Notice how many x-intercepts does a quadratic function have? One here and one here, right? That's two. How many x-intercepts does this table have? Two. Okay? So I do want to point out, like, a couple of ways you can recognize a quadratic in a table is one, the symmetry, and two, the x-intercepts. But you don't always see the symmetry. You don't always see the x-intercepts in a table, but what do you always see? Linear additive rate of change. If you have a linear additive rate of change, you have a quadratic. If you have a quadratic function, it will have a linear additive rate of change. So there's a couple ways to see quadratics in tables, but that's the big thing that I need us to recognize. Give just a couple of seconds for you to write down whatever you need to about that table. Okay? You at least need to have that defining characteristic. We don't have time to write down the whole table if you haven't already done that,
What
but
is the defining characteristic?
can anyone help us out and know what is the defining characteristic of a quadratic in a table?
Have linear.
Linear additive rate of change. That's the thing that we kept talking about over and over again. A quadratic has a linear additive rate of change. That's the only way to know every time in a table if you have a quadratic or not. You have to make sure you have that detail down. That has a linear additive rate of change.
You still gonna work on that board?
Huh?
Are you still
Can
gonna
I
work on
get
that?
this paper?
I have one more thing. Say again.
Can I get the paper?
Yes.
Stop.
I think that's- Annalise, were you not here at all yesterday?
No.
So you don't nobody no more this great. See good grade, no Koyan. You was
Penny, what are you saying?
because Koyan did not want to shake my hand. And it feels like the love is lost. It's right over there.
What love was there?
Well, we had the same fifth grade class, and it's like, just like friendship. Say something else. Say it two more times. Say it one more time after that.
Penny.
Okay. Just quit. I'm not serious, man.
I don't think anyone thinks that you're gonna actually do anything.
Literally, like.
Right.
Oh, okay. I'm being civilized, man. Like, you know, what is it? I'm having an amazing day. Can I have some snacks?
He's a lot more.
Come on, I just heard the little. Yeah, little-
No, you didn't. I ain't even finished zipping it up, and you thought I had snacks. Like,
I heard the little rattling.
no, you didn't, cause
I'm gonna have to
I was
reprint the
like,
proficiency scales because
Jaheem got
they
snacks.
got messed up.
Jaden.
Okay.
What up?
I ain't got no.
I'll get you a whole punch.
We have a napkin.
No, I didn't.
Alright, last couple of things. You should have all that down, hopefully. Not hopefully, you should. Alright, what's the last mathematical representation? Ivan. The what?
Algebraic.
The algebraic, right? So, we now need to make sure we understand algebraically. Now, this is I'm going to step you through things a little bit more. Now, remember, how do we calculate area?
A equals BH.
So, base times
Height.
height. Actually, can I erase up here
Yes.
and write it so that,
Yes, you can. She did.
No, I was talking to him. He said, he asked me something, I said no.
oh, okay. I was going to check to see if he, alright, I'm going to put all this up here so it's easier for people to see. Alright, so area equals base times height. Now, Mr. Anderson talked about it with a few different groups yesterday, that if you subtract the base from 50, don't you get the length of the height?
Yes.
Okay? So what then can I do with 50 minus b in respect to that area equation?
How do you spell height? H-I-E or H-E-I?
H-E-I-G-H-T. I before E, except,
We're in the living room.
No, it confused me.
right, I before E, except after, have y'all never heard this?
No.
Okay, so, as a general rule of thumb, there's a handful of breaks from this, but it's I before E except after C, or when it's an A as in neighbor or way.
What?
So,
That's a word we don't know.
man. Okay, so, niece, that's I before E, right?
Yes.
Okay. Trying to think of another word that has an E and an I at the same time.
France.
Peace, yeah. Did you say France?
No, friends.
Friends. Notice all of these with I's and E's together, it's I before E, right? Okay. I can't think of one where there's a C first, but if that C was before the I and the E, it goes to EI. And then,
What you said it was before?
yeah, if the C had been before. But notice here with way, it's EI. Neighbor, it's EI. So, I before E, except after a C, or when it's an A, as in neighbor or way.
Do you know how to
right?
spell Wednesday?
Yes.
That's confusing to me.
Wait, is it W-E-D-N-E-S?
D-A-Y.
Bro, hey,
Yeah.
I've been thinking this like
Zed day.
W-E-S.
I think it's
W-E-D-N-E-S. Alright, let's get back to the math though, okay? So, area equals base times height. Height is 50 minus the base. So what can I do with 50 minus the base?
Minus 50 again.
Well, remember, I'm talking about in respect to this equation. I can remember when x was equal to 1 earlier, what did we do with that 1?
Multiply. We added x.
We didn't add it.
We
We
substituted
substituted that 1 in for
before.
the x, okay? Not for the 4, and for the x. 50 minus the base is equal to the height, right?
Yes.
So what can I do with 50 minus the base?
Multiply.
What?
Oh my God. Subtract.
Dog, what did we do with that 1? We substituted. So what are we going to do with 50 minus the base? We're going to substitute. That hasn't changed. It stays the same. If 1 is equal to x, I substitute 1 in for x. If 50 minus the base is equal to the height, I'm going to substitute it. So that height becomes 50 minus the base. Here is the first principle that we need to recognize with quadratic equations. Okay? And I'm actually going to just rewrite this. I'm going to switch the order.
So,
I'll explain why in a second. if I were to just graph this equation or this expression right here, what type of function would I have? What type of function?
No, linear.
Is it linear or exponential?
Exponential.
Okay, so if it's exponential, what
Wait,
do I
no.
have to have?
No,
Oh,
no, it's
it's
linear.
gonna be -1.
No,
No.
it's, no,
Hold on to your idea. Hold on. Guys, if it was exponential, what would I have to see?
A curve. Or
what, bro, put an
In
X.
the equation, what would I have to see?
Square.
An X.
An x where in
And
the
the X.
exponent, or a variable in the exponent. Notice we don't have any x's here. There's no variable in the exponent, it's not exponential, but -1 times b plus 50, this would be linear. If I were to just graph y equals b or y equals x, that would also be linear. That's literally the parent function. So, first detail about a quadratic is a quadratic can be a linear times a linear. Let me say that one more time. A quadratic can be a linear times a linear. A quadratic. A quadratic can be a linear times a linear. There's actually 3 major forms of quadratics. This is one of those 3 major forms. So if you have a linear being multiplied by a linear, you have a quadratic function. Okay?
Can we go back to the concave?
Bro, it's like when I
Concave
scoop
down,
that,
like
you
frown.
scoop forward.
What does that mean? Okay.
It's literally right there, my guy.
So that's the vertex.
No, concavity is the whole shape. That's concave down, it's going down. The vertex will be a maximum, but it being concave down just means that the whole thing overall is going down. Notice it's down like a frown. So if it looks like a frown, it's concave down. Notice it's going up. Can I pour water in it and the water stay there?
So only 10.
So it's like a
If it don't have
cup, and if it's like a cup, it's concave up.
So I'm gonna test you and ask, which way is this concave?
Yeah, what's the concavity? You gotta recognize it. Okay, final detail. If I were to distribute this, the area is equal to -b squared plus 50b. What's right there in that form that tells me it's quadratic?
Square.
The square. So, a square in standard form, we'll talk more about what standard form is later, but a square in standard form
It's quadratic.
is quadratic. Okay. We've got to recognize that there are many different ways to write a quadratic equation. We're going to talk about something called the standard form. We're going to talk about that linear times a linear called a factored form, or you can even have what's called a vertex form. And so what I need us to recognize is that if you have one of those forms, it's quadratic. But you have to recognize the type of form as well. So while you're getting your final notes down there, I'm going to pass out a sheet of paper, which that's going to end up getting erased, so you need to make sure you have all your notes down so you can apply this later in your small groups.
This explanation. This is quadratic. This is linear. This is explanation. These notes.
I wanna do this. I wanna do
This is practice.
Okay.
Okay. So once again, I want to remind y'all a little bit of how I operate is I present you a problem, then we go over it, and I point these things out. Did y'all know all of these details about the linear or the linear additive rate of change when you work through this problem?
Wait, what?
Did y'all know all these details about linear additive rate of change when you work through the problem, guys? No. Did you know about all these features necessarily when you work through this problem?
We should have. I mean, like.
We should have known a lot of these.
You shut up.
But,
Don't
hey,
get mad at me because you don't.
excuse you?
Yeah,
That ain't
excuse her, cause I'm not dumb.
No,
Let's
no,
start
boy,
here.
Stop. We done. We done. We're both.
Now y'all gotta
I
argue.
hate
Boy,
bull. I hate
listen.
bull.
Y'all gotta argue now.
Hey, Ivan, chill. You don't need to add to it. Listen, guys.
That's not nice.
It's on the word.
Brianna, you didn't have to add into
No,
it.
it's
not.
I know, everyone knows it's
That's
not.
not
Ivan. And hood off. Ja, hood off. Don't put an extra hood on.
Let 'em fight.
Jaden, hat off. Like, golly.
Ready to take this ski off and listen to them people.
Hood off.
I'm trying, Mr.
No, you ain't.
Taking it step by
Jason.
step.
Jaw.
I know.
Y'all get away with this
Cause you
thing.
don't wanna run it.
Okay. Now it's time to practice applying these things. Oh, what I was gonna say is, legitimately, Chelsea's not wrong. Most of this we should have studied. I will say most teachers do not go into that linear additive rate of change. That's probably something new for just about everybody. But the parabola and the features of the parabola, we've probably seen that before. Maybe this idea of a linear times a linear may be new, but a lot of that is still stuff we've done in the past. But we still need to practice it. We need to master it, okay? All the stuff with parent functions, I know y'all always made like I was crazy, and the transformations, all of that was done in Algebra 1. It's not brand new information, okay? But we still got to master it. At this point, though, you have a couple of sheets, and it's not going to take that long. I know it looks like a lot, but all I want you to do with these different functions is what?
Right. No, write the equation.
Nope.
Table.
Dog,
What type of
read the
function?
directions.
Tell us what type of
What
function
type of
is it
function?
linear, exponential, or quadratic?
Okay, so what type of function is shown in each representation? So linear or exponential or quadratic. Justify your answers thoroughly, okay? So I do want y'all to work with each other. I will give you a choice. Do you want to sit at your desk or do you want to work at vertical surfaces? How about this? You as a group decide. If you as a group want to sit, you as a group can sit. If you as a group want to work at a vertical surface, you as a group work as a vertical surface. What I want you to do, yes, hey, please listen. Stop and listen. What I do want you to do is, I want you to do all of numbers, say 1 through 4, and have all of those on the board together. Do not erase until I come over and have a discussion with your group. Okay? Same thing with numbers 5 through 8. Okay? So let's get up, let's get going. Yes, you can erase that board.
You ate your eat mine.
I ain't eating
What the
nothing.
fuck is that off-brand drink?
Who got
the sun drop?
on St. George?
Who got on Sandra?
Everyone's been burning.
They got off-brand joint.
Hey guys, it's been less than a minute. We're already off task. Let's get on task. Right here. That's not how the size I want to make that. Hold on 1 second. Excuse me. This will also give you a little bit of time to add some notes in. Now, number 1 right here. One of the most common things that students like to do with number 1 is they like say, oh, it's a linear function because what rate of change, Dean? Why did constant additive? Okay. Now here's the thing. A linear function does have a constant additive rate of change, but if you look at this graph, no.
Linear.
Only linear functions have a constant additive rate of change. Remember, a quadratic has a linear additive rate of change. Okay, here's my point that I need y'all to understand. If you are just looking at that graph, do you know what the rate of change is? So you can't say this is linear because it has a constant additive rate of change. You don't know that. Now, Walter, what did you do that allowed you to know the rate of change?
I'll look for the points on the graph.
Yeah, if you look at these points here, it's -7, was that 5?
There was 0, 2. Oh yeah,
-7, 5, 0, 2, and 7, -1, I think.
Yeah.
Notice, if you did this, don't forget change in y and change in x. Now, can I make the argument that it has a constant additive rate of change?
Yeah.
Yeah. Alright. So, but notice, until I actually find the constant additive rate of change, you can't make that, okay? I want to make this more clear to help y'all build up your capacity to explain these things. I've mentioned something called CER in class before. This is a model used in English and science a lot of times. It's called the claim, the evidence, and the reasoning. Your claim is that this function is linear. Now, if you are going to say my evidence is that it's a constant additive rate of change, what do you actually have to have found first?
The table, or like.
The table or the constant additive rate of change, right? That's not the evidence we have. What is the evidence that we have based on that graph? The graph is a It's a line. You don't even have to say straight. The graph is a line. That's my evidence, my reasoning. Base your evidence that you put on there on what you have. Now, here's what we could then say. So, the function has a constant additive rate of change. Okay? But notice, I have to base my justification on the information that I have. We know that it has a constant additive rate of change because it's linear, okay? Now, from there, what are the next two? Exponential. I need you to be careful with the exponential because one of the most common things that I see students say is, oh, it has a curve.
It's not touching the line.
Okay, so the asymptote's important, but remember, this right here is a curve, isn't it? So why is this not exponential?
Parabola.
Because that curve is a parabola. These curves are exponential curves, okay? So when you're looking at numbers 2 and 3, this is an exponential curve. And what is something that a lot of people are saying that has an asymptote? With a horizontal asymptote. And so that's how we know these two are exponential. Finally, number 4 is a quadratic, and what's the evidence for the fact that it's a quadratic?
Parabola.
The graph is a
X minus symmetry.
Yep,
X
so
and Y equals X.
graph is a parabola. Note, as Dean is talking about, what is this point right here? Or these points?
X-intercept.
Those are x-intercepts, right? Where's my y-intercept?
At the top left.
Top left, on the y-axis, that's my y-intercept. My axis of symmetry is right here, or line of symmetry. And then what's down here?
Vertex.
That's my vertex. I know we can't see it perfectly, but it's down there. There's something I was going to say with this. Yes, that's it. Those are the features that you want to recognize, okay? So it's a quadratic, it has those features. What questions do you have about this function? Okay. Please have that annotated, work with each other. Now, let's move on to the second page, numbers 5 through 8. Okay, so 5 through 8 at this point. I'm only going to give you about 5 minutes to work on these, so let's get after it.
Wait, we can erase it, right?
You can erase it now.
I say Gator out of all the names.
It's
John,
over them.
I swear, listen,
Stop.
look at my work. I'm literally doing my work.
You can do work and play dumb games. Quit
But I'm
it.
not playing dumb games. I'm having a problem.
But John, I have seen you throw stuff before. Quit.
I threw it at her.
John,
I ain't throwing
don't throw anything. Like, pick up a pencil, do something productive. Right? Okay. So,
I would be lying. Wait, I was
Wait, what? I'm not lying.
You going along with it, somebody want me.
alright, I want y'all to look at these really quickly. So, it's been about 5 minutes. I think number 6 and 7, pretty straightforward. Number 6 is what type of function?
Number 6 is linear.
Is linear because
The line.
the graph is a line, okay? Number 7 down here is what?
That's a
Quadratic, because the graph is a parabola. That's good logic, right? Make sure you practice identifying your different features. This is going to be important in the next lesson. So we've got x-intercepts here. What do I have right here? What's this point?
That's y-intercept.
Y-intercept. That's the intersection with the y-axis.
That's the vertex at the top.
Vertex at the top, because remember our vertex is our turning point, okay? And then what line goes through that vertex?
Line of symmetry.
Line of symmetry, right? There's symmetry around that line, okay? So,
Bless you.
hopefully, we're good on 6 and 7, but I need us to look at the rest of these. Because, and Brianna, that means we need to put down that book.
My lady.
Brianna!
Bro,
She knows she ain't reading that hard.
Language. Brianna?
She ain't reading that
I'm
one.
guessing that it's supposed to be a prop to play the card. Is that fair?
No, I started reading this book yesterday.
She
Okay,
ain't reading
but
that.
please put it down so that we can focus on this. Because I'm about to address the most important misconceptions that we had.
She reading
Okay.
preview.
So, number 8 here. A lot of us said that this one is quadratic. A lot of us did. But I need y'all to pay attention. This is the graph for number 8 right here. This is the graph, right? That's 9, 20. That's 12, 14.
linear.
That's 8, 15, or 15, 8. Yeah, that's as linear as it gets, right? So, let's investigate this one again. To go from 20 to 14, we're subtracting 6, subtracting 6, subtracting 6, subtracting 6. Make sure you also check your inputs. Notice that's plus 3. On both sides, the change in y and the change in x is constant what? Additive rate of change. So, I know, and I like the wording over here, y'all talked about a second difference, but do I need to go to a second difference here? No. It's constant additive rate of change, and what type of function has a constant additive rate of change?
Linear.
Linear. Notice the table and the graph are telling the same story. We need to remember that multiple mathematical representations is powerful. Check them. Check not just the table, but also a graph, and investigate it that way. So, number 8 is definitely linear with a constant additive rate of change. Does anyone know, by the way, what the constant additive rate of change in number 8 is? And I'll give you a hint.
6.
It's not minus 6.
It's 3.
That was
It's
it.
not plus 3.
What number?
It's a negative 2. Malia, where did you get negative 2 from? Yeah? Yeah? Ah, so you kind of looked in between here. Okay, I'm going to give you an even easier way. Okay, let's keep our mouths shut if we're not going to say anything respectful. Is that clear?
Oh, you talking to them?
Whoever it was it Jaden that said that?
Oh my God.
Regardless who it is, you need to be respectful. Put your food away. Why do you have food out? What are you chewing? Like I'm watching you chew.
Did you put no God away?
Hey,
No, I said
bro.
I ain't said no code word.
Shh. Right here. Focus. So, we said this was linear. Constant additive rate of change. Does anyone remember what the name of the constant additive rate of change is? What was the name of the constant additive rate of change? The name for the constant additive rate of change.
That's the,
So it was an arithmetic sequence, okay? What? Let me go back for a second. What's the equation for a line? The most common one that you want. Y equals mx plus b. Where is the rate of change in that equation?
B.
MX.
B.
Oh, the slope.
The slope. I need y'all to remember, how do we show repeated addition? Through multiplication. The m is my slope, that's my constant additive rate of change. And one of the most prominent ways, the way that I calculate slope every time, is the change in y divided by the change in x. What's my change in y over here?
6.
Not 6,
Two.
negative 6. What's my change in x? 3. What's negative 6 divided by 3? There's my function. Okay? Or my slope, sorry.
You
So,
divide the y and the x.
so, well, you divide the change in y by the change in x. Remember, it's rise divided by run.
So the M
Notice
will
I
be
can check it right here as well. Down 6 to the right 3, negative 6 divided by 3 is negative 2.
So the negative 2 gonna be M.
That's our slope, yes. Guys, I do want to pause and point this out. For anyone who's like, man, Mr. Kenny, this is whatever. But how many of us struggled with linear and exponential functions the first time around? So how many of us still need to show me that you can do a linear and exponential function? So that's why we're going over this right now. So that you can build up your understanding. Because I don't care when you learn, but I do care that you learn. You've got to master this. We need to be on the lookout for slope when we talk about a linear function. Now, let's come over to number 5. I think a lot of us recognized, as far as I saw, everyone said, hey, it's exponential. And we talked about the fact that it was multiplying by 3 halves. But this is the most common place that people struggle with exponential. So let's talk about this one. Remember, when you have an exponential, because I know a few key points, or a few key people, Finney, put it back, you can get it later. A few key people definitely know how to find the constant factor here. But when you have an exponential, when you think you have an exponential, you're constantly, repeatedly what? Multiplying, right? Let's pretend like no one has found the constant factor yet. If that's true though, 4 times whatever my factor is equal to what? 6. 6 times my factor is equal to? 9 times my factor is equal to? 27 halves. You can take any set of those and make a quick equation. 4 times my factor has to equal what? 6. Hey guys, how would I solve that equation? How would you solve that equation? Right.
Like, yeah.
And you know what 6 divided by 4 simplifies to? 3 halves.
Wait, so we don't know.
You think it's exponential, you don't know what the factor is. Take a value, multiply it by your factor, you get the next one. And then check it. 6 times 3 halves, that's 9. 9 times 3 halves, that's 27 halves. So your constant factor there gets you there. Alright, so we should have our stuff updated through number 8. What I now want you to do is work on the next page, numbers 9 through 12. Let's take 5 minutes as well to get the types of functions in 9 through 12.
I don't know. I don't act like if I don't know.
Well,
Exactly.
I ain't gonna say that.
About these. Alright. Hey guys, it's been 6 minutes, so let's start talking about this one. So, 2 things. First things first. It hurt me when Dalton. Ow! Walter! Put my chair back! You shouldn't even have it! No, you don't! Go Okay. So, first things first. Man, that hurt my shin. Yeah. That actually hurt. So, I'm gonna erase this that was up here.
Can you might need to sit down for a little minute?
No, I got stuff to teach. Alright, number 9 here. Walter or Dalton actually took the time. Listen, Walter took the time to do what?
Make a grab.
Make a grab before he tried to murder me.
Walter's trying to get you going, man.
I know, he's like, I hate Mr. Kidney. I'm gonna kill him. Alright.
That's funny.
There you go.
Alright, so -3, -12 is right here. -2, 0. -1, 1, 2, 3, so
Get mad. I never get
0, 6. 1, 0. Y'all good over there? Notice, if I look at this right here, what shape do I have? Well, what shape? A parabola, right?
Oh, that's quadratic.
So it's a quadratic. Notice right away, like sometimes tables are harder for us to see what the type of function is, but right away when I see that graph, it's like, oh, that's definitely a quadratic, right? It's a parabola, okay? Now, look at this table again though. So, well, one, I heard someone talking about this 0, 6 being the vertex. But is that 0, 6 a vertex?
No,
No.
it's on a symmetry.
It's not the line of symmetry. What is this 0, 6 right here?
Stop talking about
Notice my turning point, my maximum's actually up here. That's my y-intercept. Hey guys, I'm trying to help you learn something and we ain't locked in. We gotta fix that. That's my y-intercept. A key detail to notice about a y-intercept, what do we know about every y-intercept? The x is 0, okay? Now
So
remember,
like 1 would be like the bottom would be 8.
correct, yeah. Because the y is 0. So this is my y-intercept. This is my x-intercept. Notice, what else do I have?
You got another.
I got another
Why? No.
X.
Yeah.
x-intercept. Hey, what type of function had two x-intercepts?
Quadratic.
Well, a parabola does a quadratic, right? So notice that's another important detail to say, hey, it's probably a quadratic. Now, notice though, right here, that's not my vertex, because what do we have around the vertex? There's an S word. There's symmetry. So my vertex had to be somewhere in between. Notice graphically, is my vertex in between those 2 points?
Yeah.
Yeah, right? So my line of symmetry is in between here with my vertex. So notice we're identifying these different features. Okay. Now, here's the thing. Just taking a table, making a graph out of it, makes it really easy to see all these things. But I do want you to be able to look at a table and know what type of function it is as well. So, I'm going to erase this. Hopefully you have those notes down already, because I need the right-hand side of this table. To go from negative 12 to 0, what's happening? We're adding 12.
Adding 12.
To go from 0 to 6.
That's 6.
Adding
To go from 6 to 6.
That's 0.
Adding 0.
And 6 to 0.
Negative.
Minus 6. And be careful, because I know at least one group, and this is a very common thing, where they said put plus 6, but 6 plus 6 would be 12, right? It has to be 6 minus 6. And if you don't do that, you're going to miss out on the important part here. Okay? So Victoria, to go from 12 to 6, what has to happen?
Uh-oh.
You got to what? You're going to add what? You said add?
To go from 12 to 6.
Yeah, so from 12 to a 6, what do we have to do?
Stop talking about No.
So we all agree?
And 4.
12 plus 6 is 6?
No, I'm gonna.
Negative 6.
So minus 6. Be careful, right? Okay? Notice to go from 6 to 0. Minus 6. 0 to negative 6.
We said negative.
Negative 6. So, notice this orange is constant. Orange is what? Constant additive. Hey guys, if that second difference is, which that's the way Amaya keeps talking about it, and that is a very common way to talk about it, I just didn't use that language. The constant additive is here. What's always to the left of constant additive? Linear. So, this purple here, it's an additive rate of change, but what type of additive? It is a linear additive rate of change. So what type of function is it?
Linear.
It has a linear additive rate of change, so quadratic. Please notice, the table, the graph in multiple ways is telling the same story. 2 x-intercepts, that's quadratic. A line of symmetry, man, that's quadratic. Linear additive rate of change, man, that's quadratic. The graph is a parabola. Guess what? That is quadratic, right? There's power in mathematical representations that you don't get if you just try to memorize 1 or 2 things. Really pay attention to this. It's time to learn something.
Literally.
Okay? I want you to look at the table in number 12. What things should jump out at us right away to give us a hint without doing any work?
It got
It had 2x. It had 2x.
Oh yeah, we got 2 x-intercepts right here.
Now I realize you got 2, if it has 2 x and so it's gonna concentrate down.
Not always. Not all parabolas have x-intercepts.
Yeah, I want it.
Okay? They all have a y-intercept, correct. But notice, those are both concave up. This one doesn't have any x-intercepts, this one has 2. Heck, this one only has 1. We're going to talk about when each of those things can happen soon. But yeah, so just 2 x-intercepts doesn't guarantee it's concave down. That's just what we've seen a lot.
Can
Okay?
it be a minimum vertex?
The vertex can be a minimum. That's what we just saw with all the graphs I created. Okay, does anyone see anything else in this table really quickly?
Yeah. I already did it.
Okay, where do you see the y-intercept? The 0, 6. Notice with a y-intercept, the x is 0. With an x-intercept, the y is 0, okay? I see another really important point in this table, though. The -2, -2, what does this need to be? the vertex and where my line of symmetry is. Because you see it, yeah, so vertex and line of symmetry. You see how there's symmetry right here? Okay? So all that's telling the same story. Now, also check your rate of change.
The constant additive is plus 1.
No, plus 10. So when I look at the second differences, it's plus 4. Constant additive right here in my second differences. So that purple, that rate of change, that additive rate of change is what? Is linear. So what type of function do we have?
Quadratic.
Quadratic, okay. So telling the same story all the way through with all these details. So please pay attention to those things. We'll talk about the next two really quickly, and we'll just end with this today. Monday we'll pick up with the different forms of a quadratic.
Yes, sir.
Right? But we still have a couple more things to do, so don't put that away because we got 10 minutes.
Ooh,
Just
that's
we want the rest of
vacation.
these. All right. Yeah, 10 minutes. All right. So I want to talk about numbers 11 and 12. You should have already talked about these. And Dean put number 11 in the calculator. He said, "Hey, is this cheating?" And I said, "It's not cheating, but I do want you to be able to look at number 11 and know exactly what type of function it is without looking at the calculator. I also want you to be able to graph it without looking at the calculator. Hey, what type of function is number 11? How do we know this is exponential? Okay, so this is an exponential function because x is in the exponent. Now, some of us definitely need practice making graphs and tables with these, and so that's why I have this on here as a practice thing for you. Now, what I do want to point out is this. When we look at this exponential function, this a times b to the x, what should we hopefully remember about a and about b here? What should we hopefully remember about a and b from this exponential function? Dude, we just said it's exponential. Okay, let me ask a different question. Ivan, John, focus. But remember, this is an exponential, right? Hey guys, what does an exponent tell us to do?
Multiply.
Not just multiply. What type of multiply? Constantly multiply. So what are we constantly multiplying by? The b, but look at the equation. What are we constantly multiplying by? 1/3. Right? The variable exponent x tells us to constantly multiply by 1/3. Okay, that's important. If we're constantly multiplying by 1/3, what is that 6?
Joe, why are you doing hand sanitizer?
The y.
The y?
The y what?
Intercept.
Y-intercept. My starting point. That's where we're starting. It's time to learn. So if I'm thinking about a table, and I want you to make a graph, but I'm thinking about a table, my y-intercept is 0, 6, and what am I doing to that y-intercept? Constantly multiplying. Oops. And so what I will also remind you is, at this point, so some of us are like, how in the world do I graph that? Haven't we spent a lot more time now doing inputs in to get outputs out?
Yes.
Could you take the time to do f of -1 equals 6 times 1/3 to the -1? Yeah, okay. Guys, there's lots of strategies available. You don't have to just do one method. I like the y-intercept and the constant factor. But if you need, Jaw, am I teaching or not?
You are. I'm listening to you. He just talking to me. I don't know why.
I'm not even talking this with crazy.
Dog, if I go back and watch the video, I'm going to hear your voice on the camera. Like, don't try to gaslight me. You're in the wrong. Fix it.
Go back and read.
So, inputs in to get outputs out. Number 12. This one typically throws students off a little bit because it's not the normal way we're used to seeing it. But first off, is it exponential?
Yes. No.
What would he have to see for it to be exponential?
Exponent.
An exponent that is the...
Exponent.
Yes, we have to see an exponent that has a what in the exponent?
X.
An x or a variable, right? You have to say it's a variable in the exponent because If it was quadratic, what would I see in the exponent? A 2, right? So we have to be careful and clear now. It's not just an exponent, it's a variable exponent or a square in the exponent, okay? So it's neither of those. What is this probably then? Probably linear. And it's a little bit different than what we're used to, but hey, what's happening between 3/4 and x? They're being,
Multiply.
oh yeah, isn't multiplication constant repeated
Addition.
addition, which is linear, right? I can rewrite this as 3/4 x minus 12. That might look more familiar. But it's the multiplication that's really important here. Note,
Coming to you with today's announcements is Memphis Drake.
we want to understand change in y and change in x.
Please stand for the pledge.
Okay?
Attention, salute, pledge.
Y
I pledge
intercept.
allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Notice I can add the 3/4, Dean, like you were trying to do. But Dean, you can't see what I just did.
Promoting safety.
I can add the 3/4, or I choose the change in y and the change in x. So I'm adding 3 to the y and 4 to the x. Okay?
What did NASA use to build the moon? AstroTurf.
Okay. So, leave this out because I'm just going to quickly touch on 14 and 15 and 16 before we leave because they usually end a little early. So just leave this out for a second.
5th quarter, a game plan for Grace. Join us
Put
for
that up,
food,
right?
fun, and fellowship following your
So I don't know what
Friday
this
night
is.
football game tonight from 10 p.m. to 12 a.m. at East McFarland Baptist Church. Students, please listen up for exciting updates from the Hillcrest Pages debate. Our team has been rejuvenated and we will begin regular operations immediately. We will have hard work. We have been at hard work defending our identity and are proud to share our mission statement.
Futures for the teams remember the mind of tomorrow's winners. Cultivate the skills of our nation's doctors, presenting logical argumentation. Prepare students to believe and
Hey guys, just wait.
This is your last chance to find out. Anyone interested in joining the team must submit this competition through our process. The deadline to sign up is the end of the week, which is today. That's room 305 to submit your comments by the end of the week. Please don't go away. Study time. There has been an update to soccer practice.
Girls soccer trials will be on Monday, October 27th, directly after school at the football stadium. Please see Coach White in room 400 if you have.
Boys soccer trials will be on Monday, October 27th, Wednesday, October 29th,
Yes, sir, Walter.
Thursday, October 30th. Directly after school, the practice field event. Please check. Please see Coach McDonald's room 211 if you have any questions.
Am I on here? Hey guys, tonight our football team takes on Oak Mountain at home. And we're saying educate the Eagles. So wear your best. I mean your best, because I have on my best, nerd versus jock. Or you can just wear the color with it. And as always, make sure you are in dress code. Let's get ready to cheer on the
Like
pack
you do
and
know it's
educate those
already
Eagles.
Friday, so like you're already dressed up for now.
Have a great day.
Or not.
The choice is yours.
Alright, right here, number 14. What type of function do you think 14 would be?
I think quadratic,
Why quadratic, Ivan?
because the x's are, like this, yeah.
So, yes.
Isn't that problem supposed to repeat because you get 2 in the front? Or am I tripping?
So we'll talk about that too later, but right now, I just want to point out, if I just graph x plus 2, what type of function would that be?
If we just grab what, x plus 2?
Just x plus 2.
That'd be
So I got a
right?
linear times a, so what type of function should this be?
Quadratic.
This should be a quadratic, hold on to that, okay? So linear times a linear would be quadratic. Let's look down here, okay? Number 15. What type of function would number 15 be?
Quadratic.
Why quadratic?
Isn't there a 2 in the?
It's square.
Is that an x? or
Okay,
is
that
it
square is a huge hint that this is probably a what?
quadratic?
A quadratic, okay? What about number 16?
Linear.
Why linear?
I don't know, I just,
No exponent?
oh.
Okay, so there's no exponent. So if there's no exponent, Could it be exponential?
No.
No.
If there's no exponent, could it be quadratic?
No.
No. Okay, so note if I distribute here, I'm left with this.
What is it? It's quadratic.
Coriana, please don't ever turn your back towards me again and try to sneak things that you know you're not supposed to sneak. Just because I can't see it doesn't mean I don't know it.
Door.
So, we will pick up Monday, working through these.